Hello, calculus students. Welcome to another online lesson. We are continuing our discussions on applications of derivatives. Specifically, we're going to deal with some real-world applications or slightly more real-world applications of our derivatives. Talking about something called optimization. Optimization is the idea of finding a maximum or minimum, also known as an optimum value. For example, we may be looking to find a minimum cost of production. Or we might be looking for a maximum size possible, or minimum amount of time, or perhaps maximum amount of time, or maximum amount of profits, or minimum cost. These are all, again, different things that we could deal with, minimums and maximums. So sometimes we want it to be the highest value possible, other times lowest. Now, how do we find this optimum solution? Well, knowing that they're maximums and minimums, we can utilize what we've been discussing with regards to derivatives. For our derivative, if we set it equal to 0, we're then able to use that in conjunction with a sign diagram to find our maximum or minimum value. And depending on what we're looking for, we can then find the best or optimum solution, the highest or lowest, depending on what we're looking for. Another thing to keep in mind is that the maximum or minimum does not always occur when the first derivative is 0. That sounds crazy. Well, let me give you an example here. If we have cubic shaped curve like this. We would have a maximum here at A and a minimum here at B. And I always call them maximums and minimums, but they're not really maximums and minimums. They're relative maximums and minimums, meaning that A is higher than anything immediately to the left and anything immediately to its right. It's the highest value in that little area. B is the lowest in its little area, anything immediately to its left or immediately to its right. However, what about this value here of C? Is that not on the graph, and is that not lower than B? It is. And so it really comes down to your window. If your window or domain were to include that value, this relative minimum is not the what we call global maximum or minimum. It is just a relative minimum, and our actual lowest value might happen here. Or let's say our domain went up to this spot, so this could be our highest value, which is actually higher than our local minimum or local maximum at A. So that's just something to keep in mind. Does it happen very often in this class? No. But again, it's something that certainly can happen, and we should certainly be aware of that. We want to make sure that when we're setting up our problems, we get our variable in terms of the thing that we're trying to optimize, and I will demonstrate that on our next two examples. All right, please bear with me on these next two examples. They are a little bit vast, and so I will try to keep things as clear and efficiently moving forward as possible, but it's possible I may stumble at some point. So we're starting off here by talking about a cake dish. It's made by cutting out squares from the corners of a 25 centimeter by 40 centimeter rectangle. That would be this rectangle right here. So 25 obviously being the short end, and the 40 being the long. And then we cut out these little squares from each of the corners, which allows us to then be able to fold up these edges right along this line here, and fold this one right along that edge and this edge, so on and so forth, so that it turns into this three-dimensional cake pan with an open top right here, and then these sides, like if I call this side A or face A, that would have been folded up from this, and face B over here would be folded up from this, so on and so forth. So that's the idea of what we're dealing with here. We want to know what size squares must be cut out in order to produce a cake dish of a maximum volume. So first thing I'm going to start with is a volume equation. So volume, I know, is equal to base times height times width, or length times width times height, or however you want to call it. I'm going to do length times width times height. My length I'm going to refer to as the long side, the width as the slightly shorter one, and then my height would be the height here, so length, width, and these heights. And you'll notice that the height, which would be like this blue line right there, is exactly the same as the size of the square, or one side of the square that was cut out. So I can label that as H here on this particular diagram. That's a lot of variables. I've got a v, I've got an l, I've got a w, and an h. And really the thing I want to be talking about is the size of the square, which is really only my h variable. So I'd like to rewrite the other two. Now what do I know about L? We said earlier that this whole length here is 40 centimeters. And this whole length going this way is 25 centimeters. But we're going to end up cutting out some parts of that. And the part that we're cutting out is this square. But you'll notice we cut out that part on both sides of our L. So if this is h, and then we have h over here, my new length is going to be this 40. Take away that h, take away that other h. So I can rewrite L is equal to 40 minus 2 h's. Now my width, the same deal. It started off as 25 centimeters, but I'm taking away this h here, and I'm also taking away this h right here. So there's an h getting subtracted and another h getting subtracted. So my width is going to be equal to 25 minus 2 of those h's. So let's rewrite this now, all in terms of h, the variable that we're trying to optimize. So we have volume is equal to length, which is 40 minus 2h, and width is 25 minus 2h, all times h. So that's length, width, and height, all rewritten in terms of h's. I may want to go ahead and expand this with a little FOIL. We can see 40 times 25 gives us 1,000, and our outer and inner terms will become negative 160h. I'm sorry, 130. And then our last terms here, the negative 2 and the negative 2, become positive 4h squared. But then I have to take all of this and multiply by one more h, so we end up with volume is equal to 1,000 h minus 130 h squared plus h cubed. And I have written now my expanded form of my volume expression in terms of h. So what's the first thing we want to do? We would like to do our derivative. So we want to know where there are maximums and minimums. So we're going to do our derivative, set it equal to 0. So v prime now, my derivative of volume, is equal to, first term will be 1,000. Second term, I bring my exponent out front, multiply with the negative 130, so I get negative 260h. And I lost my 4 from earlier, so there should have been a 4 here, and there should have been a 4 here. Sorry about that. And so when I do this derivative, I get 12h squared. And again, that came from bringing the 3, multiplying it with the 4, and then lower the exponent by 1. So that's my derivative. It might be helpful to rewrite that with our variables first, descending order like we're used to. And what do we want to do with this derivative? We want to set it equal to 0. All right, so 0 is equal to 12h squared minus 260h plus 1,000. From here, you can utilize the quadratic formula. It's a nice quadratic. You can also factor. I'm a big fan of factoring, and even if you're utilizing the quadratic formula, I'm going to show you how I factored it. And so the first thing I did was I took out a 4, which left me with 3h squared, and then I had minus 65h plus 250. So I divided 4 from both sides. Obviously 0 divided by 4 stays 0. Now I can rewrite that with its factors. My first terms both have to have h's in them, and one of them has to have a 3, so that 3h times h will end up giving me this 3h squared. My last term has to multiply to become 250, but I can see there's a negative involved, and so they probably both need to be negative here. And I need to come up with terms that multiply to be 250, but when I do FOIL, will give me a middle term of negative 65. And through a little guess and check, we get 50 here and negative 5 here. So when we do FOIL, again, we would be doing 3 times the negative 5, which is negative 15 h's, and here I would have negative 50 h's, which add up to become the negative 65 h's. So I have done my factoring. I set each of those factors equal to 0. And so I have 3h minus 50 equals 0. Add 50 to both sides. I get 3h equals 50, or h equals 50 over 3. And then on the other side, a little bit simpler, I just have h minus 5 equals 0. Add 5 to both sides. So h equals 5. Sorry, my equals didn't line up there. All right, now we need to make a sign diagram with these values. And so we make a number line. The only two numbers we're putting on the number line are the 5, which is the lowest of our two answers, and the 50 over 3, which is approximately 16 2/3, so just a little bit less than 17. We need to know which one's our maximum, minimum, and using a sign diagram can help us with that. So numbers to the left of 5 on the number line would include 0, which is my favorite number to plug in. 1's also good, but 0 I think is even better. So I'm going to go back to this derivative expression right here. I'm going to plug in a 0. If I plug in a 0, I get a positive 1,000. So that's very positive. Now, in between 5 and the number 16 2/3, 10's there. 10's a good one to plug in. So if I plug in a 10, I would have 1,000 minus 2,600 plus 1,200. And you would see that these guys combine to become 2,200. They're positive. The negative 2,600 is a greater absolute value, and so there's more negative than positive, so we would have a negative answer. And you don't even have to actually finish these problems. You just have to decide, is it positive or negative? And last but not least, I need a number bigger than 50 over 3. 20 is a good one if you're going to actually show the work, but I'm going to pick something really big like a billion. And if I plug a billion in right here, I'm going to have a billion squared, which is a whole ginormous number. It's going to be very positive, and there's going to be 12 of those ginormous numbers. Whereas here, if I plug a billion in, it's just going to be negative 260 billion still. So that's not nearly as big as the amount of positives I have. So this is going to be very much positive. All right, so now where do we have a max and where do we have a min? We're really only concerned in the largest volume, and so maximum. Well, here we're going up on our slope until we get to the 5, and then we go down. So this would be our maximum right here. On the other one, we were going down, and then we went up with a positive slope. So 50 over 3 is our minimum. H equals 5 is our maximum. So how big are these squares that we're cutting out? They are 5 by 5 squares. And cutting out a 5 by 5 square will maximize the volume of our cake pan. All right, let's do one more. All right, for this one, let's see if I can maximize my space here. Find the most economical shape, minimum surface area for a box with a square base, vertical sides, and an open top, given that it must contain 4 liters. Liters. So we should be quite familiar with a lot of metric stuff, but honestly, my conversion on liters is not great. So I ended up having to look up how big a liter is. And a liter is 1/1000th of a cubic meter. Or you could say it's 1,000 cubic centimeters, interestingly enough. So I ended up working with the 1/1000th of a cubic meter. So 1 liter is equal to 1 over 1,000 meters cubed, cubic meters. All right, so let's see what we've got here. We have 4 liters, and so that would be equal to 4 over 1,000 cubic meters. Or you could write that as a decimal of 0.004, 4 thousandths. Now our base, it says, is square, and they showed that with these tallies here to make sure that we can see that they're all identical. It has an open top, and we're talking about minimum surface area, So how do we find surface area? Let's start there. So area of our surface is going to be equal to the square base box, and let's call that L. And so it would be L times L, which would give us the area of that. So L squared plus the sides that we have here, and there's going to be 4 of those, the front, back, left, and right, and that's going to be L by the height. So L times H, and again, there are 4 of those. If I add those together, that would end up being my surface area. Too many variables. I need to rewrite these using just one variable. And I know that overall the volume of this needs to be 0.004 meters. So I'm thinking about everything being in meters in this problem. So off to the side, 0.004 cubic meters has to be equal to my volume, which would be length times height, or length squared times height. We could really utilize either one. I'm going to put it all in terms of L. So I'm going to solve for H here so I can replace it with L's. 0.004 meters cubed is equal to L squared H. To get H alone, I divide both sides by L squared. Let's cancel out, and H is equal to 0.004 over L squared. So I'm going to rewrite my surface area problem as L squared plus 4 times L times 0.004 over L squared. We can clean that up a little bit, and we can say that my surface area is equal to L plus, if I distribute the 4 here, that's going to become 0.016, 16 thousandths, all over a single L, because this L and one of those L's will cancel out. And I lost my squared here. Okay. Looking good, I think. So now I think it's time for a derivative, which will be A prime, which is equal to 2L. And this guy we can think of as actually being L to the negative 1 power. So instead of plus, I should probably have a minus here. Minus 0.016 L, and then we lower the exponent to a negative 2. So we could rewrite that now as 2L minus 0.016 all over L squared. And that would be our derivative. We want to set that equal to 0. So now we have 2L equals negative 0.016 all over L squared. And we would like to solve this. Well, obviously, I can't make this part actually equal to 0, because if I divided by 0, it would be undefined. So what I'm going to do is I'm going to, let's move it up here, and I'm going to move this negative stuff here to the other side of the equation. So I have 0.016 L squared, and now it's positive, equals 2L. And I'm going to multiply both sides by L squared to get rid of those. And I'll multiply L squared over here as well. So now I have 0.016 equals 2L cubed. Divide both sides by 2. So now I have 0.008 equals L cubed. And I need to essentially cube root, or take everything to the 1/3 power. And I do know the cube root of 8, because 2 times 2 is 4 times another 2 gives me 8. However, there's 3 decimal places here, so the first one must have only had 1 decimal place. And you can check this on the calculator, but that means that L must equal 0.2 meters. And so I think at that point, we have optimized this. Now, 0.2 meters could be rewritten as 2 decimeters, or more likely 20 centimeters, if you'd rather do that as well. But we had our original answer in meters. So what did the actual question ask? It said, find the most economical shape, minimum surface area. So we could go back and take this 0.2 meters or 20 centimeters, whichever we prefer, and plug it back into our area formula. And since we have length already, we could literally just put it in here. If you want to figure out what the height is, we could take our L and go all the way back to this problem right here, which says take 0.004 cubic meters and divide by 0.2 meters squared, and we could find h that way as well. And I believe you end up with 40 centimeters, but you can check that on here, 0.4 meters. But anyway, that's the idea of our optimization on this problem. I think more difficult than anything on these problems is the setup, but there's a lot to keep track of with your variables and everything like that. So we do have some problems in the book you can take a look at on page 431. This will be our last video lesson before our test on applications of derivatives. Till next time.